Good morning, all of you. My name is Manish Range. I am an engineer of Sri Ramdev Baba College, Engineering of Management, Nagpur. As an engineer, I am studying about a lot of things, and one of them I am studying about a topic known as classical and quantum billboard example, in which we use a simple ball for finding the probability of classical as well as quantum gates, in which we use some calculation stuffs or other things. So, which are we been studying about further. So, let us start with the topic. First, the introduction that I've been studying in these topics are the first. The Billboard problem is a model system used to understand physical dynamics. Means it is nothing but finding the probability of moving a particle from one position to another position, in which we will using some complex numbers or some real numbers that I might use. So as I had told you that we will differentiating between classical distributive system and quantum uncertainty. As I know that the classical deterministic system is analog for studying chaos, and the wave mechanic is study for quantum uncertainties. There is nothing that much difference. Classical distribution system is used for calculating real values, while the quantum uncertainty is used for calculating complex values, which are not possible for normally to calculate it. Now, our first topic is classical billboard ball model. In this, a ball is being said that the particular initial point by which it is been moved around all places by Newton's law of motions, in which it can collide with walls, in which it can lose its energy, not lose its energy, or maybe energy coming. But in billboard model, the energy is been conserved. There is no loss of energy, due to which its initial conditions are predictable. Now, as, as I tell you that the momentum is conserved, no energy is lost. Therefore, it have a complex geometry, which we are studying about further. So, the classical dynamic equation by which can tell that the energy is conserved or not is simply this, which we have studied in 12th class. Force is equals to mass into acceleration. As we can say that this classical dynamic equation has been used for classical uh, classical probabilistic systems. So, or we can say classical deterministic systems, which give us initial position and vector future position, which has been fixed at the points. Now, I told you that energy is conserved, so therefore this is the formula, and here is maintained that it is remain constant, which tell us that the energy is been conserved. Now, now with a simple probabilistic system example, we can tell the sorry, billboard, bill ball example solutions. Now, we can see that there are four initial points located at some positions. So I consider zero be the initial points from where it is been rotating, or we can say changing its positions. So the first of all part that will be performing here is to create an adjacent matrix by which we can get the overall way of this. And as it is a classical probabilistic system, the probability between particles have been given. So therefore, probability from going 0 to 1 is 1 by 2. So in adjacency matrix, we calculate the probabilities. So as we go from up to down vertically, so the first position belongs to zero position, मतलब initial position. Second position is of one position. And third position, sorry, third position is of second position. It is a little bit confusing, but not that much. And the last position, which is fourth position, belongs to third. Similarly, on horizontal side, 0, 1, 2, 3. Now, probability of going from 0 to 0 is obviously 0. There is no saying that 0 is being going back to its own place. Now, probability going from 0 to 1 is now probability of going from 0 to 1 is 1 by 2. So obviously we have right 1 by 2 here. Now, as this position is third and this is 0. So from 0 to 3 is, you know, there is no pathway or any another thing which are connecting these 0 and 3. So obviously it is 0. But we have missed this part 1 by 2 in which it is 0 and it is 2. So the probability of going from 0 to 2 is 1 by 2. So that is we say 1 by 2 is been written over here. Similarly, another adjoints have been taken out like that. This is from probability from 0 to 1, sorry, 1 to 0. This is probability of getting from 1 to 1, where from 1, there is no probability from going 1 to 1. It is 0. Similarly, for going from 1 to 2, for 1 to 3. Similarly, here also for fourth conditions or means second conditions from going 2 to somewhere, in which here from going 3 to somewhere. Therefore, this is the adjacency matrix that we found, and this is the major point because in further, with help of this adjacency matrix and stages, we can add several stages at any instance. So first of all, we take this matrix as the initial stage of our classical probability system. Now, this is a column matrix due to which transpose has been applied here. Now, multiplying this uh, adjacency matrix in this initial state, we get a new state. At that state, we called it after one time click. After one time click. So, multiplying these both matrix, we get the third matrix. This is that is this. This is also column matrix. So basically, we what do we do row column multiplications and add it simply. So 0 into 1, 0, 1 by 2, 0, 1 by 2 into 0, 0, 0 into 0. So overall, the first part of the matrix is 0. Second is 1 by 2. Third is also 1 by 2 because at first position it multiply with 1 which give 1 by 2 and all of the rest are multiplying with 0 which gives us 0. So at second and third position we get 1 by 2 and at fourth position also we get 0 because at that position it is obviously that 0 into 1 0 and 1 by 2 0 1 by 2 and 0 and 0 0. So that are the things. We have now the new initial state rather than initial state, and they have a difference in them both. As we can see that in initial state, uh, probability is with 1, but in this it is 0, and the rest of all 0, but in this it is similar. So the initial state is been differing from new state. Now we will use this new state to find several more new states after every time clicks. So we will multiply this new state with our adjacency matrix to find more new states like we have done here for finding two time clicks. So we multiply this matrix with the new states to get a new states that is 1 by 2, 0, 0, 1 by 2. So what happened after this? We get another matrix state, third, third, third time click after four time clicks, continue to growing, due to which helps us to tell the classical probability systems that what is the probability of going from this position to this, coming from this to this, from this to this, which help us to find it more accurately. Now, now let us summarize what we have studied in classical uh, probabilistic system, in which what things are being studied. Now, as we can see that we have learned the states of system corresponding to column vectors. As we stated that we learn about initial state, new state after one time click, new state after two time click. Also find the adjacency matrix in which the column vectors are being major parts. Also find the dynamic of system to the matrix where it is deterministic system or probabilistic system. Third, to process from one state to another, obviously one time click, two time click, we must multiply state vector with matrices. Okay. Multiply state dynamics are obtained in Y multiple matrices that are being done. Now, let's talk about the new fresh topic, which is quantum Billiard Ball model. In this, we are not talking about any real values. We are talking about complex numbers, complex values, or in short form, we can say wave packets. Ball is replaced by quantum wave packets. Here, we are not using any kind of balls like we are doing in classical billiard ball examples. Name are similar, but we are using packet wave packets. Or now, as we are using a quantum, but again, the Schrodinger equation is also appearing in this. So therefore, this is the Schrodinger equation form E psi is equals to minus h dash square upon 2m v square psi. This is the classical psi equation. A boundary continues confines, the boundary confines the wave function psi x comma y. Now we will study about it more deeply. Now the visualizations which are we'll be finding on the quantum billboards are standing wave patterns formed due to boundaries reflections. In quantum states, the reflections are being bounded analogs to quantum confluent in potential well and more of that. Experimental examples like quantum dots, microwaves, resonates, and all of that things which are been studying. So it is the overall visualization or overview of what the quantum billboards are been doing. Now, the quantum classical corporations, correspondence. So in this, the semi-classical limit, which is h dash, is zero. But in quantum motion, approximately classical territories. In this, uh, the semi-classical limits of h dash has been removed out and the approximately become classical territories. And other things are that quantum scar that demand a classical path divisible in quantum probabilistic distributions and more of the things. Applications. The applications that have been used in quantum billboards are microwave billboard for testing quantum chaos, quantum dots, which are known as cross products or dot products, generally in 12th language, optical cavities, mixed billboard system, helps understand quantum to quantum transition and chaotic systems and more on the things. Now, as we come to our first example of quantum billboard ball, so let us read. Let us revisit the stochastic billboard ball example. This time we shall make a quantum system out of it. The quantum billboard balls. Consider the graph. Now, this is the same as the classical billboard ball, but in his, we are not using any kind of real numbers. We are using complex numbers. Like you see, it is 1 upon root 2, which is a complex number, irrational number, as I say. So here also will do the same thing, finding adjacency matrix, finding probability from going 0 to 1, 1 to 0, more of thing, finding the same new states from initial state after every time clicks. Same things have been happening here as what's been happening in in classical billboards. But the difference between both two are that in classical billboard ball, we use real numbers, but in quantum billboard ball, we use complex numbers, which have been difficult for understanding by the computers. So as we can see that here the probability of going from 0 to 0 is always 0, from 0 to 1 is 1 upon root 2, and from uh, 1 sorry 2 to 0 is 1 upon root 2. Similarly, same conditions that are been applying in classical quantum sorry classical billboard ball, same. But the main factor is that in the main factor is that we are using unitary matrix in quantum computing or quantum billboards. So let us start with a single marble on the vertex 0, the stage 1 0 0 0. It is also transpose, so therefore it is a column matrix. After one time click, the system will be in the state 0 in the root 1 by 2, 1 by 2 0 transpose. Now, reflecting the 50-50 chances as the static billboard example, as this is a complex number, so it have 50-50 chances of getting both the values. So it have 50% of chance that the particle will move to another particle, or it will move around its own. But what happened if we multiply this vector by A? A is another matrix, okay, which is determined to the next state of the system. A quick calculation will show the after the new time click, the system will be back in the state 1000 T. This is in stuck contract to what happened in with the stochastic billboard example. Here the other path cancel each other's and interference. We should have seen this by noticing that in the order to find a state after one time click, we should have had a multiple hour starting. Now, as we know that unitary matrix is been using in this quantum billboard example, that is A multiplied by A. However, A multiplied by A is equal to A square or identity matrix. This is the main concept of his quantum billboard example. Now, now the final part of the these PPTs are that we are comparing both the cases, classical as well as quantum billboard. So in classical probability system and quantum probability system, the first point is that in both we find adjoint matrix. In both we find marble at on the state with uh, vertex 0, vertex 1, means in both cases we start from initial point as zeros. And in both cases we have obtained new state after one time click, after two time click, and so on. But the major difference between those two are their probability. As we can see, here is a real value and here is a complex value. So classical probability system works on real value and quantum system works on a complex values. Now, now let us review what we have learned among all these PPTs. So state in constant system are repeated by column vector of complex numbers. The sums of module square is work. The dynamic of quantum system is represented by unitary matrix and is therefore reversible. The undoing is obtained wise. The algebraic inverse. The adjoint of the unitary matrix represents forward evolutions. The probability of quantum mechanics are always given as the module square of complex numbers. The quantum state can be superpose means it can interfere in within it. Physical statement can be more in this statement. Basically, uh, some state are similar that others. Now the conclusion of the final part of this PPT is that classical billboard shows deterministic chaos, while quantum billboard exhibit wave interference and quantizations. These both things have already told by me in starting of the PPT. As you know, in this we learn the gap between classical and quantum mechanics, okay, which is the bridge gaps. As as I tell you that in classical we use real value, quantum we use complex value. So this is the major point which create a gap between both these mechanisms. So now these are some references from where I have to the notes and explain and write on this PPT, combining all these PPT theories from another different books or websites. I make this PPT. Also, our college professors PPT. Some PPT's information is also present in this PPT. Without his help, I can't do that much of things. So thank you. As it is the last page of my